Hello viewers, so welcome back to the course on matrix computation and its application. So today we are going to discuss the lecture 8 and we'll going to start with the generalization of the intersection of the vectors, intersection of the subspaces. So in the previous lecture we have discussed that we have two subspaces U and W, and then we have showed that these subspaces, if I take the intersection, then this is also the subspace of V that we have discussed. So today we are going to discuss the generalization, that what is going to happen if I have a n number of subspaces. So in this case also we have the U1, U2 up to Un, the n subspaces of V, then their intersection is also a subspace of V. So from here I can say that U1 intersection U2 intersection U3 Un. So that is the, I am taking the intersection of all the n number of subspaces. So it shows that this is also a subspace of V, and proof is similar, that you just take the one element, two elements, and then show their vector addition and scalar multiplication belongs to this one, the same way we have done, and then we can show that it is a subspace of V. So now I want to give you example that how it look like. Suppose I take a subspace U be the set of all vectors. So I am taking the set of all vectors showing as x1, x2, xn that belongs to Vn. So this is the vector I am showing. So sometimes we also show the vector like this one, x2, x1, x2, xn as a column vector. So this is just a column vector, and here I am showing as a row vector, but it is a vector. So let U be the set of all vectors that belongs to the satisfying satisfying the three equations. So let I take the equation as a1 x1, a2 x2, an xn, that is equal to 0. So this equation I just take the equation number 1, then I take b1 x1, b2 x2, bn xn, that is equal to 0, second equation, and suppose I take one more equation c1 x1 plus c2 x2, cn xn, that equal to 0, equation number 3. So basically I am taking all the sets of vectors which is a solution of this linear equation. It is just the linear equation, and I will solve this linear equation and I will get the solution. So I am taking the U as a solution set of these equations, the system of equation. Okay. So this is, I can call that here U is, so U is the solution set of system of linear equation 1, 2 and 3. So it is a system of linear equation, and we know that it is n number of vectors are there, n number of variable, and 3 equations. So, infinite many solutions are going to happen. So, in this case we are taking that, and this is a homogeneous part. So, it is always going to have a solution. So, that set I take as a U. Now, what I am doing now is I will take U1. So, U1 I am take that is the space, is a set of vectors satisfying only equation 1. So, I will choose only that elements which satisfying only first equation, that is it. Similarly, I choose U2, the set of vectors satisfying equation number 2, and from U3 set of solution satisfying equation 3. Now, I can find what is U1 intersection U2 intersection U3. So, in this case you can see that in this case I am defining the set of solution or set of vectors, not the solution. I can just write the vectors here. This is a vector, set of vectors satisfying the equation 3, set of vectors satisfying equation 1, 2 and 3 together. Okay. So, and this is, you can check that this is equal to U. So, this way we can define the intersection of the sets. So, and I know that U1 is a subspace, U2 is also subspace, U3 is also subspace. I am just taking the intersection that satisfies all these conditions, and that is equal to my U. So, this way we can define that how the intersection is going to play a role here. So, after this one we are going to define the another thing, that is we call it the direct sum, because just now we have seen the U plus W at the sum of two vector spaces. Then just I want to go little bit further and I want to show what is the direct sum. So, in this case that if, so what is that? We know that for any two subspaces, suppose let U and W, U plus W is also a subspace of V. That we have already seen. Now, if in addition I find U intersection W, because we also know that the U intersection W is again the subspace. So, in addition if we found U intersection W and that contains only the 0 element, that is the trivial subspace, then U plus W is called, so in that case we can call it a direct sum and can be written as u w. So, it is just the summation and putting the circle, and this is the notation of the direct sum. Okay, so, whenever we write the direct sum, it means we are able to write the summation and the intersection between these is only the 0 element, not any other element. So, let us take one example. So, let I take V 3, okay, that is equal to R 3. So, from here I just choose u I take as xy plane. It means set of elements x, y, 0. So, that x and y are the real number. So, I am choosing u at this one. Then w I am choosing, that I choose it maybe yz plane, or maybe I just remove this xy plane and the yz plane. So, yz plane is a set of all the elements 0 y z belongs to R. Now, in this case you can see that if I discuss about u intersection w, then I have the xy plane, that is just xy plane, and then we have a yz plane. So, yz plane, and whenever yz plane and xy plane cuts together, then it is going to happen. So, in this case we have only y axis, because we get a line and that line is the y axis only. So, xy plane and yz plane, wherever it is intersecting at the y axis. So, we will get only y. So, it is a space and it is not equal to only the 0 space. So, in this case from here I can say that if I define u plus w, then is going to be is not a direct sum. Okay, because the u plus w will contain set of all linear combinations of the elements of u and w. Okay. So, and this is not going to be the direct sum. Now, what is going to happen if I take, so again if I take u as xy plane and w as z axis. So, in this case if I take u intersection w, then you know that xy plane and z axis they cut only at the element 0 0, not any other element. So, in this case I can say that from here then u plus w is just, it will combination x y 0 a plus b 0 0 z where A and B are the scalars, and this will equal to, I can write as Ax, or maybe I can take any element from here taking the linear combination. So, I just remove this A plus this. So, I can write this as a x, y, z. So, if I take x, y, z, where x, y, z belongs to R, belongs to R. Okay, so this is, I am getting this one, x, y, z belongs to R, and this is equal to V 3, because it is containing all the elements of V 3. So, from here I can say that U plus W is a direct sum, and this is equal to V 3. So, we have splitted the V 3 into two parts, in the two subspaces. One is x y plane U and another is W. So, this is called the direct sum. We are dividing the whole vector space into the two subspaces, and these two subspaces has nothing common except the 0 element. So, this is called the direct sum. Now, after this I just want to define one more term, one more definition. Just let if U is a subspace of a vector space V, I just take a U is a subspace of the vector space V, and let small v I am taking is a vector of V, then we are defining this V plus U, and it is set of all the elements V plus U, where U belongs to U, set of all the elements I am taking. So, I take all the elements, okay, and this is called, so when then this is called a translate of the subspace U and the subspace U by V, or it can also be written as a parallel of U, or it is also called a linear variety. So, basically what we are applying here, suppose we have some subspace U. So, let us, I am taking a subspace, I know that the subspace always passing through the 0 element. Suppose this is my subspace, okay, and suppose I am taking this V, I am just defining R2, and U I am taking a line passing through the origin. So, this is my x and this is my y. Now, I take element, suppose I take a element as 1 0, then V plus U, basically we are getting 1 0 plus U. So, if I am going to represent that one, so this is x and this is y, and so this is the point 1 0. So, this line will shift here and will pass from here. So, this is the element 1 0. Now, from here you can see that this is my translation of u by this point, this one, and so this is definitely is parallel to this line u. But from here you can see that now from here I can say that this is, from here I can say that v plus u need not be a subspace of V, because we can see that in this case 1 0 plus u does not contain the 0 element, and for the subspace it definitely should contain the 0 element. So, does not contain the 0 element. So, which implies that 1 0 plus u is not a subspace of V. Then how we can say that it is a subspace of V? So, from here I can write that if V, if the V belongs to u, then V plus u is always a subspace. Okay, so, in that case we can say that this is always subspace, otherwise V plus u, that is the shifting, is not the subspace of V. So, this is also one of the important property we wanted to discuss. Now, so after this one, now we just want to discuss one more term, is that a very important property, that if S is a non-empty subset of V, then span of S is the intersection of all subspaces of V containing S. So, this one is just the extension of that, because in this case what I was saying, that if S is a non-empty subset of V, then this is belongs to the intersection of all the subspaces of V, because just now we have discussed the intersection property. So, now it is I can prove it very, because we know that S always belongs to span S, that we already know, and we also know that this span S is the smallest, the smaller subspace, contain S. Okay, so, whenever the S is there, this span of S is also there in that subspace. Okay, so this is so now let I have subspaces, suppose S1, S2, Sm, these are the subspaces. Of the subspaces of V containing S, which implies that, so if I am taking this one S1, S2, Sm are the M subspaces of V that contains S, which implies that span of S also is also contained or belongs to S1, S2, Sm. So, that is also contained in S1, S2, Sm. And from here I can say that the span S will also belongs to S1 intersection S2 intersection S3 intersection Sm. So, this will be contained in all the intersection of this one. So, that is just we wanted to show. Now, let us do one example. Find the intersection of the given set U and W. So, U is given to me x1 and x2, that belongs to V2. So, this is I am taking one of the subspace of V2. So, I need to check whether it is subspace or not. So, find the intersection of the given set U and W and determine whether it is a subspace or not. So, I am taking U here and W is I am just choosing x1 and x2 that also belongs to V2 such that x1 is less than or equal to 0. Now, let us do this one. Now, in this case my U is a set of vectors x1 and x2 belong to this one, where x1 is always greater than or equal to 0. So, that type of U I have taken, and this is we have taken where x1 is always less than or equal to 0. Now, let us check. So, it means U will contain all the elements. So, U will contain this which type of elements like 0, 1 and maybe 4, 0, 3, 1 like this one. But if I have the element -2, 0, so that does not belongs to U. This we have to keep in mind. Okay. Also, 0 0 belongs to U, that is there. So, first we have to check that whether U is a subspace or not. So, in this case I just take -5, if I take any element alpha, and that is suppose I take -1 and I multiply by any element from U. So, alpha into one element I choose maybe x1 and x2, okay. Then it will be equal to alpha x1 alpha x2, and suppose my x1 is 2 and x2 is 1. So, that belongs to you in this case. Now, if I take this element, then definitely -1 into 2 1, it will be -2 -1, and it does not belongs to you, because I am choosing my x1 is always greater than equal to 0. So, from here I can say that U is not a subspace of V2. Similarly, because this alpha is coming from the real line, so it can be anything. Similarly, W also, so in this case also it is less than equal to 0 I am taking here. So, I will, if I multiply by a negative sign, it will be positive in that case. Also does not satisfy the scalar multiplication property, which implies that W is also not a subspace of V2. So, in this case neither U is a subspace nor W is a subspace. So, we cannot discuss their intersection even. So, this is the example we have done. So, let me stop here. So, today we have discussed some properties like a direct sum, and then we have discussed about the translation of the vector of a subspace by a vector, and then we have discussed few examples. So, before from this we will continue from this in the next lecture. Thanks for watching. Thanks very much.